Good afternoon. Great to be at ASA. My name is Perry Marshall. I'm from Chicago. 22 years ago, I went to China to visit my brother. He was a missionary. He had a seminary degree. He was teaching English, and he had been there for 4 years. And he said, Perry, I don't believe this stuff anymore. I'm not a Christian. I'm quitting my job and going home. And I'm done with this Christianity stuff. And we're both pastors' kids. And we were having some existential arguments for a long time, and he was dragging me with him, but I didn't expect that. And we got into an argument, and I said, Brian, look at the hand at the end of your arm. This is a nice piece of engineering, and I'm an engineer, I should know. You don't think this is a random collection of accidents, do you? And he goes, hold on. And he came right back. All you need to get a hand is random DNA mutations and natural selection, and you'll eventually get a hand. And I just stopped right there and I thought, that does not sound right to me. I've never heard of that working anywhere else, but I know a bunch of biologists would nod their heads and agree with him and not me, and I've never studied this. I'm not getting anywhere in this argument. I'm going to shut up and I'm going to go home and I'm going to figure this out. That is actually why I'm here. It was because we had this argument in this bus 22 years ago. And I had no idea how deep and fascinating this question was going to become. And the only biology I had ever taken was high school biology. I didn't like it. I was an electrical engineer. I had designed the speakers in the Jeep Cherokee and the Honda Civic. I had written an Ethernet book. I had been a manufacturing engineer at Kellogg's. I had done a lot of things. And I thought any theory of evolution is a theory of engineering. And I'm an engineer, so if this is valid, this should eventually make sense to me. So I started buying books and obsessing about this, and I went as deep as I possibly could. And after a while, I started to get my bearings, and I started to understand the terminology. And the deeper I went, I had two opposing tensions. One of them was, as far as I can tell, an evolutionary narrative appears to be true. I see lots and lots of anecdotal evidence that would suggest common descent and adaptation, all of that. I have no problem with that. But the story I'm being told of how this works doesn't make sense. I'm an engineer. I build things for a living. If you've ever been in a profession where if a bunch of products are coming back in pallets as warranty returns and you go into a design review meeting and you get your head bashed in, you have an appreciation for how carefully engineers design things. And I saw design in biology. And in like these, everybody made it sound like these two ideas were incompatible. And in fact, I was appalled, especially in the popular books that you would go buy at Barnes and Noble. I was appalled at the intellectual slop that passed for science in evolutionary biology. The explanations were vacuous and smoke and mirrors. And I suddenly had an epiphany when I discovered Barbara McClintock, Lynn Margulis, James Shapiro, Conrad Waddington, Evelyn Witkin. It took about 2 years to get there, but all of a sudden I discovered an enormous vein of literature that was very well documented that shows that organisms cut, splice, rearrange, re-engineer their DNA, respond to hostile situations at enormous speed, do merger acquisitions in real time, hours, not millions of years. And I was like, why isn't anybody talking about this? And so I ended up writing a book called Evolution 2.0, which came out in 2015. That has led to all kinds of interesting things. It led to a $10 million prize for the origin of the genetic code, to co-founding the Cancer and Evolution Working Group of the American Association of Cancer Research, which has 5,000 members. It led to me co-founding a cancer early detection startup a year and a half ago. I wrote a paper with Cy Gart and Stu Kaufman a year ago. And it was a springboard off of, this is Eugene Wigner, and he wrote a paper in 1960 called The Unreasonable Effectiveness of Mathematics in the Natural Sciences. And in this paper, it's almost a meditation on how beautiful and incredible it is that in physics, everything obeys mathematics. And that there are discoveries that were made in mathematics 150 years ago, somebody with nothing but a piece of paper, and suddenly that exact same thing appears in particle physics, and it works perfectly. And he's meditating on the beauty of the correspondence between physics and math. And one day, Cy Garton and I were talking.
At a meeting of ASA.
And Cy said, we need to write a paper called The Reasonable Ineffectiveness of Mathematics in the Biological Sciences. Because unlike physics, and I'm an electrical engineer, so I totally get physics. In biology, there is almost no equation that is always true. Almost none. And we published this in Entropy. And I want to explain the rationale behind this paper because I think this reveals a bottleneck that's been going on in science for about 100 years. So in life, in the world, I see three very different levels of causation that exist. The first level is physical chemical laws, and those are the things that Eugene Wigner was talking about in his paper. Gravitation and electromagnetics and waves and all the things in physics that very often exact equation, exact answer. And that is one level of causation. And as far as I know, if you go to a dead planet with no life on it, that is the only kind of causation that you will find, as far as I am aware. But then there's another level. So these are universal laws, and change over time within these laws is order to disorder, entropy. Then the second layer is logic, symbolic logic, like we have in computers or DNA. Symbols, communication, computation, languages, machines, algorithms, genetics. That occupies a middle level. And as far as we know, these laws are not derivable from physics and chemistry. Nobody knows how to derive the genetic code or English or any other language from the laws of physics and chemistry because the symbols are freely chosen. And they are local rules that are local to a system or a culture or to a cell. And under those rules is deductive and deterministic. There is one output for a given input. And that's how the middle layer works. And also, codes are subject to noise, which is information entropy, which has the same math as thermodynamic entropy, but is not the same thing. Then there's the highest level of causation is cognition, which is choice, which is at least somewhat synonymous with consciousness. Agency, action of self-interest, meaning the ability to create codes is the ability to choose local laws. Cognition is inductive reasoning, not deductive reasoning, which I will get to in a second. In other words, it is choice within uncertainty. And change over time is disorder to order, which is negentropy, which is a term that Erwin Schrödinger coined in 1943 in his book, What is Life? I raised $10 million from private equity investors and organized a $10 million prize for the origin of the genetic code. We announced it at the Royal Society in 2019. That's me with Dennis Noble, who is a fellow of the Royal Society and an Oxford professor. Seigat said there are almost always exceptions to any proposed biological law. And there is no precise, I want you to hear me very carefully. In biology, there is no precise definition of life. species, individual, gene, allele, inheritance, intelligence, sentience, function, or fitness. None of those things have a precise definition. And so the conventional view, the story that you're always told, is that the laws of physics and chemistry somehow coalesced and there was a lucky RNA strand, and then we had code, and then the code started self-replicating with self-replicating cells, and natural selection kicked in, and eventually we got cognition and consciousness. So they're saying that you can get from the laws of physics and chemistry to the laws of codes, and then those will eventually get you consciousness. There is no example of either of those two steps ever happening in any of the literature. Now, I believe that it is possible, and it's why we have a $10 million prize. The prize is not a joke, and it's not a taunt, but I think we have to discover new principles of how the universe works in order to solve that. All of the causation that we know and understand is from cognition to codes to chemistry. In life, the gene does not just build the cell rewrites the genes. And there is an M.C. Escher-like hand drawing a hand way that life works. And it's not just upward causation from chemistry up, it's downward causation from cognition down. In the genetic code, the code controls the chemistry, not the other way around. So there are two kinds of reasoning. Deductive reasoning says all men are mortal, therefore Socrates is mortal. It goes from the general to the specific. Inductive reasoning is when you go the opposite direction. It's when you go Socrates is mortal, therefore all men are mortal. It is a generalization. Computation always runs from the general to the specific. So deduction is going from the left side to the right side. Induction is going from the right side to the left. You can't prove that all men are mortal just by knowing that Socrates is mortal. Now, when I started digging into this, I started looking for a rigorous definition of induction, and I couldn't find one. And I had to invent one. And the way that I've chosen to define inductive reasoning comes from mathematics in 1936. Alan Turing defined the halting problem. So Turing invented the idea of a computer. A Turing machine is really just a computer. And what Turing discovered was there is no program or formula to tell you in advance whether the computer is going to answer the question. Is the calculation going to successfully converge? It is impossible for there to be a general formula to prove whether or not it will get to an answer. You just have to try it. And so that's called the halting problem. A computer can only do deductive reasoning by definition. A Turing machine, by definition, only reasons from left to right. The halting problem is any time you're asking, is it going to solve the problem? Is it going to solve the problem is induction. And so I am defining induction rigorously from Turing's halting problem. Computers only do deductive reasoning, but humans and cells and tissues do deductive reasoning. Which is the halting problem, which is there an answer? So humans and cells and tissues do something that computers by definition can't do. And I think the mechanism of how they do it, which we do not understand, is really the key and the secret to life. We don't know what it is. And so cells, tissues, and organisms reason from a desired output to figure out what input will get them the output. All of us do this every day. I want lunch. How am I going to get it? You might get it a different way every single day. So Barbara McClintock discovered that cells actively restructure their genomes. Epigenetics shows that acquired characteristics do pass to offspring. Cancer cells massively rearrange their DNA. New species in weeks or months, not millions of years. That's what evolution 2.0 is all about. So when do we know that an agent is doing induction and not just calculating? The answer is when it readily solves problems for which analytic solutions are impossible. It is well known that slime molds can solve the traveling salesman problem and design a most efficient Tokyo subway, even though there is not a generalized algorithm for doing that. I don't know if any of you have gone down the Michael Levin rabbit hole. If you want to see fascinating examples of this, go to a Lex Fridman interview from last fall. Michael Levin, Lex Fridman, and listen to a 3-hour interview. It'll blow your mind. So, what if negentropy, origin of life, evolution, strong AI, consciousness, and cancer are not 6 problems? What if they are 1 problem? What is the origin of nature of cognition? And what this implies is that science cannot advance beyond where it is until it lets go of the false certainty of mathematics. And I want to close with a story. This is my absolute favorite professor, Dr. Robert Knoll. He was one of the most loved professors at the University of Nebraska. He taught an English class, and every single class was mind-blowing. And one day, he's lecturing, and he says, teenagers very often love to major in math, chemistry, physics, engineering, because those are exact answer fields. And you get multiple decimals of precision. He said, the older you get and the more mature you become, the more comfortable you become with ambiguity and gray areas and not exact answers and politics and imperfection. And he goes, it's a sign of maturity if you're progressing from the exact answers into the gray. And then he says, if you want to spend the rest of your life searching for exact answers, you can go to Indian Hills Community Church. That was the church I grew up in. That was a church my father was a pastor in. And I felt as though my favorite professor had taken a 2x4 and whacked me on the side of the head. And I spent the whole afternoon walking around in a daze. And I remember it was about 3 o'clock that afternoon. I go, wait a minute, I don't go to that church anymore. I stopped a few months ago and I go to a different church with my sister. Why did I stop going there? Because the exact answers were so excruciating exact, I couldn't stand it anymore. It was dogmatic, it was rigid. And I'm like, I'll be darned, my favorite professor just told me I'm growing up now. And I'm only 20. And he was right. I think this is where science is at now. Biology has been trying to get rid of the shackles of physics envy, which is misplaced. I love physics, but biology is a higher level of sophistication than physics. Biology doesn't obey mathematics. Biology creates mathematics. And that means there's never going to be a perfect mathematical formula that's going to tell us how cancer works, or how economics works, or how marketing works, or how psychology or sociology. There was a talk earlier about bipolar. There are not exact answers. There are heuristics and models, and there's the judgment and wisdom of choosing which data to focus on and which data to throw away, because you can't use all of the data. So let's have some questions, and I appreciate you enduring our blackout. Karma.
I think I touched on this last year when you talked. I'm not really comfortable with the concept of natural intelligence like that, but I do see your talk kind of a progression very similar to what I see with Simon Conway Morris and his studies of convergent evolution towards optimal body plan and the determinism. And I think of a directed evolution approach towards optimal body plan. Does that kind of play a lot?
Yes, and in fact, if you go back and study history, at the same time that the Wright brothers were working on their airplane at Kitty Hawk, there was like 6 other people in other parts of the world that had no communication with each other, and they were working on the exact same thing. And technology had gotten to a certain place, and all these people are searching, and they're all finding something that looks a lot like an airplane Similar, but this is how all technology works. This is how all biology works. It's why there's convergent evolution. There's only so many solutions, and biology will find them. And it's through ingenuity. It's not through random accident.
Yeah, but it's a very determined, a collected approach. I like that idea of rather than saying it's a natural selection, just a random thing. There is a directed
Yes.
push towards whatever ecological niche you're in, for example, towards an optimal body plan. Is that
Yes, and in the last 5 years or so, I've seen a remarkable openness to teleologiness and cognition in biology that used to be verboten. The whole field is completely changing. Yeah.
So in other words, perhaps I hope I'm not oversimplifying, but in other words, the assumption of evolutionary biology that things come randomly is basically incorrect, and if they view it as we see all these things in evolutionary biology, but there is some purpose behind that, it would solve a lot of the problems with statistics and probabilities, and they're actually hindering their advancement because it might be easier to assume there's purpose and then look how it advances.
Yes.
Purpose in mind instead of figuring out, oh, how long do you have to wait for this to happen randomly? And they're not focusing on the right path.
Yes, cancer is evolution running out of control.
Yes.
You will never solve cancer if you assume that a cancer cell is purposeless, ever.
Yeah.
It is just as purposeful as a terrorist.
Yeah.
It has an agenda. It knows what it wants to do, and if you don't convince it to do something else, it's going to kill everybody.
This idea I've had for many months or a year or so, is just thinking about these things, thinking about how we have certain things we could observe, how things happen within DNA, much of what you mentioned, and the interconnections and everything, but to attribute that all to randomness, and then to laugh at people who say that can't happen because it's probably impossible. That once you learn more about how it actually developed, if you assume there was a purpose behind it.
Abdicating to randomness is anti-science.
Yeah.
Yes, randomness exists,
Yeah.
but saying it's random is the end of the road. You're out of hypotheses when you declare it's random. It's anti-science.
And that may be uncomfortable for a lot of people who don't want to believe in God.
It may.
Okay, that's about to stop there, though.
Thank you.
Thank you, Perry. Appreciate it.